Today we're going to study induction. So before we study induction, we need to understand the flux, the magnetic flux. Phi B, that's the magnetic flux, is equal to the B field dot the area, which is equal to the B field times the area times the cosine of the angle between B, the vector B, and A. So this area has a vector. Let's see, for example, we have an opening. Here is an opening that looks like this. This is like an aperture. And then let's see the vector area A. The vector area is always perpendicular to that area. So here is the vector area A. Vector A. And then we have some magnetic field. This magnetic field is going through that area. Is going through. Here is the B field. Is going through this aperture, this opening. So you can see that we have an angle. Here is the angle, theta. That's the angle theta between the B field and the vector area. So this flux is equal to the B field times the area times the cosine theta. Now, let's see if the area is pointing, the vector area is pointing up like that. Here is the vector area. And then we have the magnetic field is going like this. Here is the B field. You can see that the B field and the area are perpendicular. In this situation, we have, here is the area, here is the B field, and they're perpendicular. So the angle, here is the angle theta, is 90 degrees. And you can see in this situation, we don't have flux, no flux. No flux here. And if this opening was like a vertical, the opening is like this, vertical, okay? The vector area would be pointing like that. And the B field is going like this. Here is the B field. And this B field here, you can see it's parallel to the vector area. So in this situation, we have theta is equal to 0. And cosine 0 is 1. So here we have a maximum flux. So I put here max is equal to B times A. So this is the magnetic flux. So Faraday's law, it says that if you have a change in magnetic flux, you'll create an EMF, or you create a voltage. So Faraday's law, it says E, I put here E, this is EMF, or electromotive force, which is, it's a voltage. That name force is got just stuck to it, but actually it's not a force, it's a voltage. So this electromotive force, or this voltage, is equal to minus d phi, changing of the flux, over dt. So this is called Faraday's law. Faraday's law. Put here Faraday's law. Now, if you have a loop, okay, here is a loop, or like a wire, or a ring. You have, this is a ring. And this ring is not attached to anything. It's just sitting there in space. And you bring some magnet. Here is a magnet. This is north and this is south. That magnet will give us a magnetic field that's gonna go through this area. But you should know that the magnetic field doesn't keep on going straight, it curls. So actually the magnetic field will curl something like this, and will come back to the south. Same thing here. We come back to the south, like that. So it leaves the north, the line, and then it comes back here. So what Faraday says, if you move this magnet, if you move it close to a ring, okay, you are changing the flux. The area is fixed, but the B field is changing. You see? Look at here. If you look at flux is equal to BA. The area is fixed, see? But the B field that you bring in is changing. So if the B field is changing, it means you have a change in flux. It means this phi B is changing. So if the phi B, this flux is changing, because you're moving this with respect to time. So you're changing the flux with respect to time. If you have a change in flux, you're going to create a current. You're going to create a voltage. It's like you have some battery, imaginary battery here. And that imaginary battery is generating a current. But that imaginary battery doesn't exist physically. There is no battery there. It's like you having one there that gives a current. So when you have a change in flux, you move this magnet closer to the loop, you're gonna generate a current, okay? You're gonna generate a current. Now, this current is gonna go in certain direction. The reason we have that minus sign here has to do with the direction of the current when you do the change in flux. Okay? Now, let's see how the voltage is gonna go if you're moving. Let's see, we're moving towards the loop, so we're going this way. So I put velocity here, and this magnet is going this way. So this is increasing with time. So what's gonna happen? The current in the loop is gonna go in certain direction for the loop to create another magnetic field that will oppose this magnetic field that's coming in. You see this red magnetic field is increasing. So what will the loop do? It's gonna generate a current. Which way the current is gonna go? So the current is gonna go up here. This is I, and coming down here. So the loop is like this. So the current, now I have to be careful. I said it's gonna go up here. If the current is gonna go up here, it's gonna give me a magnetic field that's gonna go to the left. So the current is gonna go like down. So let me get a ring to show you. Hold on. So I don't know if you can see. Yeah, here is the ring. You see the ring? So the current is gonna come down. It's come down this way. It's coming down like that, and it's going like this. Now why? You see, this current is gonna generate a magnetic field of its own. So my fingers, you see, is gonna go down with the magnetic field. So this ring here, if my finger go down this way, Okay, my thumb goes down this way. My fingers are going to the right. So this ring here is going to generate a magnetic field, like a blue magnetic field. I call it B prime. So this magnetic field here will oppose that red magnetic field that was coming from the magnet. So we have the red magnetic field is coming from the magnet, and this blue magnetic field, this B prime, is coming from the ring. So this is actually Lenz's law. Lenz's law we have now two laws working together. Lenz's law says the current will go in the direction to create a magnetic field that will oppose that magnetic field that's coming in, increasing. So this magnetic field is increasing as I move the magnet. The red magnetic field is increasing. You have more lines going in inside the loop. So the magnetic field is increasing. So the loop will generate a current. I made it going down here. So the magnetic field will be, B prime will be opposing that magnetic field that's coming in. And that's Lenz's law. But Faraday's law, it just says, if you bring a magnet or you have a change in flux, you're going to generate a current. You're going to generate a voltage in the wire, which means you're going to generate a current. So Faraday's law says a change in flux will generate a voltage, will generate a current. And Lenz's law says a change in flux will generate a current, and that current it will go in certain direction to create a magnetic field that will oppose that magnetic field that was coming in. Okay? Let's see, for example, if this magnet here is moving away. If the magnetic field is moving away, what's going to happen? The current is going to go the other direction. It's going to go up here, because you're losing magnetic field. As when the magnet moves to the right, you're losing red magnetic field in the loop. So the loop is going to generate a current to put that magnetic field, remember the red magnetic field was going to the left. Okay? As you move the magnet to the right, you're making the red magnetic field weak. So the loop is going to generate a magnetic field that goes in the same direction as that red magnetic field. Try to compensate for that magnetic field that you're losing. So if you try to input some magnetic field for gaining, it will oppose you. If you are losing, it will work with you to compensate for that magnetic field that you're losing. So that's what the loop does, and that's Lenz's law. Now, you have to be careful if you don't have a velocity. Let's see if we just have a magnet there. If we just have a magnet there, look at here in the equation. Phi, we have a flux because you have a field. But that when then you have a loop, the area is fixed. The flux is fixed because you're not moving the magnet, so the field lines are the same. They're not going to change. So B is fixed, A is fixed. So the flux is fixed, you get 0. So if you have a magnet here not moving, you don't get any current in the wire. No current. This magnet has to move. It can move in or out. It can also rotate. If it rotates, you're changing the line, you're changing the flux. So you're going to generate an alternating current here. Let's see if you put some axes here. And this is rotating like that. So that you can see here you're getting north is disappearing, and then south comes in. So you're going to get an oscillating current in the loop. So this rotation of the magnet will generate an alternating current. So if you take this current here, and then you hook it up to some light bulb. We have a light bulb here. Let me put here. This is the light bulb. Okay, so what's going to happen if this magnet rotates? You're going to have an alternating current, and that alternating current will go through the wire here, resistance or resistor, and then it generates power, and then you see the light. The light will come out of this light bulb. So you can maybe put here some faucet like this water faucet. Okay. And this water faucet will give water, so the water will come down, will hit here. So this one, you have a pivot here. So this thing is gonna spin, rotate, keep rotating. If the things keep rotating, you are changing the flux in the loop. So according to Faraday's law, which is here, is gonna tell you that you're gonna generate a current. Voltage will generate a current, so you're gonna have a current. So this energy that's coming from the water is gonna go into electric energy. Okay? So you have to be careful with this Lenz's law. Let me explain it more here. Here is the loop again. And then we have a magnet here. I put here north, and then I put south. Here is the magnetic field. Let me make it. The magnetic field is going here, like that. Okay. And let's see the velocity going this way. Okay. So if I move to the right, this B field here, red B field, will be weak. So I put here, I'm moving, so it's gonna weaken. Weakens. Now, what's gonna happen? The loop, you're gonna generate a current, and that current is gonna go up here. This is the outside. This is outside, that's inside. This is out here. So the current is gonna go up here. You know, if it goes up here, it's gonna generate a B field, blue B field. I put here B prime. It's gonna go like that. Try to compensate for the B field that you lose in by moving to the right. The loop is gonna go the opposite of this reduction. It's gonna go up, go like that, to generate a B field that's gonna go to the left to compensate for the B field that you lose in there. Okay. So this is again Lenz's law. Okay. It states that the current will go in certain direction to compensate for the B field. If the B field is coming in, it will go in direction to oppose that B field. If the B field is leaving, it's gonna go in a direction to compensate for that B field that if it's leaving, you're gonna lose. So you're losing the B field. So the loop is gonna generate a B field for you to compensate for that B field that you're losing. So that's Lenz's law. And Faraday's law, it just says, change in flux will create a current in the loop. Okay.